Hi, I'm Johannes Royset. With Roger Wetz, I wrote the textbook An Optimization Primer, which introduces optimization theory, models, and algorithms in a balanced fashion. Let's take a look at the book. The book is published in the Springer series on operational research and financial engineering. It includes many applications from those areas, but also applications from statistics, from engineering more broadly, as well as from economics. The book includes 10 chapters, each having something like 10 to 12 sections. The first 3 chapters introduces optimization models and the basic algorithms, including gradient descent and stochastic gradient descent, which have become so important in the context of modern applications, such as in machine learning. In chapters 4, 5, and 6, we deal with more advanced subjects, such as non-convexity and duality and associated algorithms that can come from that. Chapters 7, 8, 9, and 10 address more specialized subjects, such as the more general problems, general equations, and games, as well as how to make decisions under uncertainty, in particular when there's risk involved. And of course, also decomposition that allow us to solve very large problems through solution of a sequence of smaller, maybe simpler problems. Let's take a closer look at each one of these chapters and start with chapter 1. We remember from differential calculus that we can always take the derivative of a function, set it equal to 0, and solve it to try to find the minimum of a function. This fundamental principle goes back to Nicolas Oresme and Pierre de Fermat. And this first chapter, we discuss how this principle can be used to solve optimization problem through the solution of equations. We also talk about various applications, such as regression and data smoothing, optimization under uncertainty, and estimation and classification. Underpinning all of this, we have convex analysis that allow us to distinguish between what problems are hard and which problems are easy. We also talk about gradient descent, which is the fundamental algorithm for solving many of these problems. Chapter 2 is a systematic study of convex optimization, where it becomes important to address the fact that applications often involve non-smooth problems. That means problems that involve some sort of kinks. So what happens when we move from a smooth problem where we might have gradients, or we have gradients, to non-smooth problems where there are kinks? So in this chapter, we introduce the concept of subderivatives and subgradients as substitutes for directional derivatives and gradients that we might have in the smooth case. And this allows us to address many problems in a systematic fashion, including those, for instance, arising in support vector machine. In chapter 3, we start our discussion about optimization under uncertainty in a systematic way. There's no doubt that almost all practical problems involve uncertainty in some fashion or another. So how can we model such problems? How can we solve them? This is the subject in chapter 3. We, for instance, discuss in detail the stochastic gradient descent method, which is so important in modern machine learning applications. But we also talk about other applications, such as those related to environmental engineering. For instance, how one can prevent pollution in a lake. Of course, a lot of uncertainty associated with that, including uncertainty that comes from the weather, but also how the land around the lake is being used. Chapter 4 gets us into the more advanced subject of approximation theory and how one can define subgradients for arbitrary functions. We discuss how one can use epigraphs of functions and how one can define normal vectors to those epigraphs and use them to define subgradients of the underlying function. From this, we can get optimality conditions and, in fact, far-reaching extensions of the simple principle about derivative being equal to 0, but now for not only smooth function, but for arbitrary functions, convex, non-convex, smooth, non-smooth. Chapter 5 talks about perturbation and duality. In particular, we introduces the concept of Rockefellians, which is our way to quantify how a particular problem can be changed through perturbations. And this is important not only in the context of sensitivity analysis, but it also underpins duality, which opens up many new avenues for developing algorithms and also general insight about an optimization problem. We also talk about various applications. For instance, in the context of network analysis, we can discuss things like vulnerability of a network. Here, a road network around Washington and Baltimore. In chapter 6, we talk about the particular challenges that we have when we might not have convexity nor smoothness in a particular problem. Second order analysis, for instance, comes in as an important part in that context, as well as principles surrounding augmentation and augmented Lagrangian is discussed here, as well as composite problems, where you have problems that can be broken down into smaller pieces. Maybe each piece individually might have desirable properties such as convexity and smoothness, and how can that be used in a systematic fashion to solve new classes of problems. We in particular address a difference of convex functions because they allow us to address many interesting applications, including in classification, where one can use difference of convex functions of a certain kind to identify regions that are certainly not separable, for instance, by affine function, but maybe by more general functions, as in this picture. Chapter 7 talks about generalized equations, which are problems that arise in the context of energy markets, in traffic analysis, and in other applications where there's some sort of equilibrium principle that needs to be addressed. Chapter 8 talks about the challenges associated with risk modeling and sample averages. We know that if we want to make decisions under uncertainty, often we would like to account for the fact that we might be risk averse. How can we model such situations? And that is discussed in this chapter. We also talk about errors associated with sampling. If we don't have enough data, how much of an error do we have? So we can quantify that in various ways, including using concentration inequalities. And this gets us into the subject, for instance, of generalization error in machine learning. And we have some examples of how we can reduce or improve generalization through various forms of regularization. In particular, diametrical optimization is addressed in this chapter. Chapter 9 talks about games and more general min-sup problems. Nash games are addressed, and various formulations that come in that context. These are types of situations that we often see in economics, and we address, for instance, Walras' barter model as a concrete, well-known economics model, and how one can identify the price that might arise in a particular market. For instance, here we have prices on the first axis, and we see how the actions of the different agents will vary depending on the price that arises in the marketplace. The last chapter, chapter 10, talks about decomposition. Most practical problems, or many at least, are really large scale. And how can we solve them in an efficient fashion? A general strategy is to try to break the problem into smaller pieces and maybe solving them sequentially or maybe even in parallel, these smaller pieces. How can we do that? Well, there are several principles we'll learn in this chapter, including the famous progressive hedging algorithm that allow us to solve multi-stage stochastic optimization problems where we make decisions in multiple stages with information arriving between the various stages. Overall, the book includes more than 100 exercises that I have the solutions for, and if you're interested and you're an instructor, feel free to contact me. I will be happy to provide you with solutions to these exercises. Also, if you have any questions about the book, don't hesitate to reach out and ask me a question. Hope you enjoyed the book, and happy optimizing.